Hello everyone and welcome back to my channel. In today's video I am going to walk you through my linked list test code, which tests two different linked lists implementation that we covered in this week's lecture. We standard singly linked in lists, LList, and the tail reference linked list, TailReferenceLList. I will explain variable and operation in details, show you how each method works, and then run so code to describe its output rudely. So let's dive in right now. Firstly, we begin in the main method tree. The program prints a header saying testing standard LList. This signals that we are about to test the standard LList implementation. In the method TestListTester we created an instance of LList with the type string. At this point, list is empty, so we call the isEmpty method, which checks if the list has 0 elements and prints out the result when then check the initialize size by calling size, which confirms that the list starts with a 0 of the size. Next, we add 3 elements, first, second, and third, using the addElements method. Notice that when we called at the code traverters, the list find the end of the list isn't empty, and then attaches the new node there. Once these elements are added, we call the displayList helper method. This method iterates over the list starting at index 0 and prints each element along with the current length. You can see the list now contains the entries, first, second, and third. At this point, the size method confirms that the size is 3 and isEmpty returns false since the list now contains element. Moving forward, we test the overloaded add index and element method by inserting an element at the specified position. First, we insert between first and second at index of 1. This operation involves adjusting to nodes pointers so that the new code is placed between the first and second nodes. The update list now reflection this insertion. Next, we add lists at index 0. Here, to new node becomes the new head of the lists, and list's next pointer is updated to point to previous heads. Then we added lists at the end of the list by using the currently size as the index, which appends the elements of the tail. After each of these operations, displayList is called again, and we usually inspection the list to see that all elements have been inserted correctly. Now we move to retrieval operation. The code gets 0, get 2, and gets last index. To demonstrate how the get method retrieves element based on their index. For instance, get 0 returns the first element, and get list size 1 returns the last element. After retrieving some elements, we test the set index element method by replacing the element at index 1 with updated value. The set method returns the old value before placing it, so we print the old value and then shows the updated list, which now contains the new value at the specified index. Removal operation are next. The code removes as element from index 3 by calling remove 3. And stores the removed elements a variable which is the printed the list is displayed after the removal, allowing us to see the not have elements by calling remove 0 and the last element by calling remove list.size -1. Each removal is followed by a call to display list, and the removal values are printed to confirm correct elements were removed. Finally, the clear method is invoked, which empties the list by resorting the heads to null and the size 0. We then print the final size and check that is empty. Returns true, confirming that the list has been successfully cleared. After finishing with this standard LList, the main method prints a header testing LList with tail references. In the methods tail references LList, we follow a very similar sequence of operations, but the time on a tail reference lists intense. The key difference here is that these implementations means a tail pointer which optimize operations such as adding an element at the end of the construct time or one. We begin by checking if the list is empty and it is its size at 3 elements, first, second, and third, and then call display list to print the list contents. As before, we insert additional elements as specified in the case between first and second at index 1, next first at index 0, and last at the end using the current size as the index. We retrieve elements using the get method, update an element with set, and remove elements from various position. Each operation is printed to the console so that you can see how the tail reference implementation behaves in comparison to the started one. Finally, we clear the list and verify that is empty. The final section of the code is to compilation method. Is this method we print a detailed comparison of the time complexity for 3 list implementation. The standard LList, a single linked list without a tail reference. The list with tail reference and a list which is an array-based list we covered in each earlier lesson. For each operation such as size is empty, get index, set index element, add element, add index element, remove index, and clear. We list the best case. We list the best case and worst case time complexity. For example, in the standard LList get index is 1 for the first element, but O1 ON for the last element, because you have to traverse to the list. In constant with the tail reference LList, adding an element at the end is optimized to O1 time. The table also highlights that a list offers constraint time access for get and set because of direction array index. Truth, it might occur ON during add operation if resize is required. This comparison always is extremely useful for understanding which data structure to choose based on the operation you need to optimize in your application. Now let's talk about the output when you run this program, the console first show the test for standard LList. You will see a message that confirm the initialize state of the list, empty size 0, followed by the list constant after adding first, second, and third. Subsequence operation like insertion, retrieval, update, and removal are all displayed with clear message indicating that each step did include printing any exception that occur when invalid indices are used. The same series of messages then printed for the TailReferenceLList, allowing you to compare how each implementation behaves. Finally, the time complexity compression table is printed, summarizing the efficiency of each operation according to different list types. To summarize, this program provides a compression tests of linked list operations using two different implementations. We have been seeing how operations like add, remove, set, get, and clear work, and we have discussed the performance implication of using a tail reference versus not. This detailed walkthrough not only helps you understand how these data structures work, but also prepares you to make informed decisions when choosing the right data structure for your own project. Thank you so much for watching. If you found this video helpful, please give it a thumbs up, subscribe to the channel, and hit the notification bell so you never miss an update. If you have any question or comments about this linked list implementation or any other topics, please leave them in the comment section below. Happy coding, and see you in the next time.